did start. Hello everybody, welcome to section 2.2 where we're going to get a little more into it as far as the calculus is concerned. We are talking about the limit of a function. Let me go ahead and take those off so I don't have so much glare. Now, maybe before I even start the section, so 2.1 was sort of just barely touching base with cracking the egg open there. In 2.2, we're going to start talking about this thing called a limit. But before I even talk about a limit, just a quick little refresher on what a function is. And I'm trying some new stuff out as well. I already see a little bit of glare here. I'm trying to move the lighting around so it's not so shadowy, but also try and get it so it's bright enough so that everyone can see quite well. I guess we'll deal with that little bit of glare in the corner for now until I find a better spot for that guy. So again, I'm trying some stuff out, so bear with me here. We're all doing the best. What was I saying? Function, right? Recall a function is a relation such that each x in the domain of f, which is our relation f, which we'll call it a function once it fits this specific definition. Each x in the domain of f is mapped to exactly one y in the range of f. So what does this mean? A function is a relation. Not every relation is a function, but a function is just a relation relating to things, in our case x and y, such that each element x, which we say is in our domain of f, or f of x, is mapped to or sent to exactly one element y in the range of f. These elements x and y for us generally are the real numbers. Right? So when we study Calc 1, Calc 2, Calc 3, we focus mainly on the real numbers. You'll see a little bit of complex numbers here and there, but mostly we're concerned with real values x and real values y. So what that does is, here's a whole bunch of stuff. X on our horizontal axis. Here's a whole bunch of stuff y. Again, for us, I mean numbers, but it doesn't necessarily have to be numbers. You could map lowercase letters to uppercase letters or letters to numbers. That's kind of what we do anyway with x and y. But what it does is, and I'm going to pick on this poor function again, y equals x squared, also known as, in the function notation, f of x equals x squared. It takes our function and it sends 0 to 0, because if I square 0, the element 0 in our domain x, it maps 0 squared to the number 0, which is the y value in the range. If I take x equals 1, that's our element in the domain, 1. I square 1, it spits out 1. Now you start to see the function really do something when you plug in the element 2, which is x from the domain. You have to square it based on the definition of this relationship. When you square it, you get 4, because 2 squared is 4. Right? And it also works not just for these discrete integer values, but we know that we can use fractions in here, right? You square a half, you get a fourth, things like that. So we can visualize this by putting it on our nice Cartesian coordinate system. All of these elements x are coming from our domain, and they're being sent to the range, which is all the elements y. Sometimes for this word range, you might see maybe in an older textbook, or maybe in a slightly more advanced calculus book, they might talk about the codomain versus the range. So the domain is where you get to take all the elements from, then you have to plug it into the function and it does whatever it wants with it, and it spits out all the elements in the range. Now you'll notice here our range is anything from 0 up to infinity. We're not getting negative values, because when we square something we don't get a negative, it's always non-negative. Worst case scenario, it's 0 if you square 0. Square a positive, you get a positive. Square a negative, you get a positive. So our codomain would be all the real numbers, but the range would be very specific from 0 to infinity. I will stick to the terminology of range. We're more concerned about where these elements go, not so much about the set that we're sending them to. Just a heads up there, if you do have like an older textbook, or if you're referencing something on the internet, you might see this word domain and then codomain. Range is just a little more specific of what we want, so that's what I'm going to stick to. But that's a function. We've all seen functions, we know functions, and this is what we do when we have some sort of x value, we plug it in, and we get some sort of y value out of it. And both of these notations are quite fine. Right. That's a good notation, that's a good notation. I'll kind of flip-flop back and forth between the two notations throughout the course. Sometimes I'll be lazy and just write, hey, y equals 7x squared plus 13. And then sometimes I'll be more specific with the more clear f of x equals 2x plus 31. So they mean the same thing essentially. But when we map this x to f of x, you might see instead of a y-axis, an f of x axis, right? They're being a little more rigorous when they use the function notation, but same meaning, right? So one thing we need to be comfortable with. So we've got this nice definition. Maybe that wasn't the most rigorous definition of a function, but it lets us know what a function is. What we want to do is introduce a sort of an intuitive definition of a limit. Later on, we'll get a bit more rigorous definition of a limit, which some people like to refer to as the epsilon delta definition of a limit. That's a little more rigorous, so we'll kind of get our toes wet first, and then later we'll revisit it with a more rigorous definition. So here it is, basically the first definition, first calculus definition that we're going to get for the course. And I'm basically taking this right out of the book. I want to use the same sort of wording and everything, so that if you're referencing the book, you're getting exactly the same thing twice, rather than me kind of ad-lib it or use a different word here or there. I don't want to confuse anyone, so I'm sticking to what the book has. And one exception, but I'll tell you that exception as soon as we get to it. So suppose this function f of x is defined for x on some interval a to b, and this is the notation for an open interval, right? We'll use the parentheses, and it'll be very specific in this course when we talk about open intervals versus closed intervals, and we use the brackets. So it'll be very specific as we come across definitions. You want to keep an eye out for that. With c in the interval a to b, this is where I differ from the exact definition of the book. The book just says x close to some a on some interval. I'm going to label the interval a to b, and then I'm going to shove c as a number in between a to b. So this little notation here, if you haven't seen this before, if you've had me for trig, you've seen it, or if you've had me for pre-calc, you've probably seen it. But this literally is read is in the interval a to b. Then we write the limit, I'll just put it right here in the middle so it looks nice. The limit as x goes to c of f of x is equal to L if we can make the values of f of x, when I say values, I mean the outputs, like the y values, arbitrarily close to wherever this number capital L is. They're using the letter L because we're talking about limits, but it's just a number in our case, by restricting x to be sufficiently close to C. Or say close to C, but not equal to C. And then, read through it, try and digest it as best you can, but I think ultimately you need a picture to really put this all into the best possible meaning. So let's say we have a function, and I'm not going to be very specific about it. I'm just going to kind of draw an arrow here, draw some squiggles, and call it f of x. All right, your squiggles might be a little different. It doesn't have to be perfect. But this is a function. It passes the vertical line test. Remember that. Right? In order for you to be looking at a function, you need to make sure it passes the vertical line test everywhere. That is, exactly one element x that you choose gets mapped to exactly one element y. It doesn't go, to two places at once and fail the vertical line test. So what I'm going to do is I'm going to pick an open interval, a to b, and it could start, over here. Maybe that's where a is, and it could end over here. Maybe that's where b is. And then I'm going to pick a c that is in that interval. So these are all my x values. These will be all my output y values, or f of x, when you get all mapped. Now I'm just going to pick a random c somewhere between a and b. Well, let's choose here. It doesn't have to be exactly in the middle. Let's say this number c is between this negative number and this positive number. I'm saying numbers because 99.9% of the time that's what we're going to be putting into functions. But again, we can do a relationship between letters if we want to, or even just images. It doesn't have to be a number or a letter. It could just be something that we can relate to something else. So I'm picking a pretty random spot here, and then it's giving me some sort of output L. Now, the thing about this is, and I want to kind of highlight this with the different colors, I'll do it in green here. The limit as x goes to c of f of x equals L. That's how we say that. Right? So we say, oh no, my green is no longer with us. So we pick a blue. We say, for this guy here, the limit as x approaches c or goes to c of f of x, we want to be specific what we're talking about. In this case, it's the function f of x, is equal to L, capital L. We'll just write the big capital L. Right, so some people, when they start taking calculus, they go, oh yeah, sure, the limit f of c is L. Totally incorrect. I have no idea what you just said. Oh yeah, the limit is L. Okay, of what? Right, be more specific. If this is here on the page, you should be saying it. Right. Some people say, oh, the limit of x of f is L. X of f. That's not how you even say just this piece, right? So again, when you get into calculus, it's got to be very rigorous. We all need to be talking the same language. If I walked into a French class and started speaking really bad French, or even some words in Spanish and German, no one would understand me, right? So same thing here. We want to all get on board, and when we see this, the first thing we need to do is realize, how do I say this, right? Before you even know what you're saying, which is going to take some time to digest, at least know how to say it, so that you get that good foundation, and then you'll learn what it is. As you say it correctly, the language will make sense. So we say the limit as x goes to c of f of x is equal to L. The limit, which is this shorthand ILM, as x goes to c of f of x, this thing that we're talking about, is equal to L. You could just say is L. Right? Obviously we can get a little bit shorter with some of the things we say, but we don't want to get carried away with being too short. So what does this mean? As I get closer and closer to this value, it looks like f of c has to spit out L. But you'll notice that arbitrarily close to L, by restricting x to be sufficiently close to c, but not equal to c, which means this doesn't necessarily have to happen. This f of c equals L, there could be a hole in the graph there, but this limit would still be just fine. That limit would still exist and be L. There is a very different way of looking at algebra in terms of, what is the value f of c? You plug c physically into the function and it spits out a value y. Or you try to plug c into the function and it can't spit out a value because c was not in the domain of that function. Right? But we're saying that this function is defined on this interval a to b, and that's why we're not getting into too much trouble here. But I just want to start off by saying, when you see that word limit, what you really want to do is think about approaching c. Approaching c, which means you're getting really close to this value c, but you're never actually using the value c, right? Not equal to c. You just have to get arbitrarily and sufficiently close to see where this function is going. I don't need to see what's happening at the letter c to know that it's coming to this value L eventually. Now, is that always true? Not necessarily, because what if this function has a hole in the graph here, and we've seen this in college algebra and pre-calc, maybe even trig. A piecewise function could be defined such that at c, the value is up here somewhere above this output L. Now you have a function that approaches this value from the left and from the right, but again, we are not concerned at c, not equal to c, which means the value could be somewhere else. Well, what is that limit? It's still L, because you're sufficiently close to c, but not equal to c. So it's telling you the limit is where do I approach, and it looks like I'm approaching this value L here. But what could really be happening at the point when x is c, that could be somewhere else, or it could be completely non-existent. Again, I'm staring down there because my laptop's down there. I should practice more on staring at the camera. So right off the bat, when you start thinking about a value of a function, that is, you plug this thing in and it spits something out. Or maybe it doesn't, because that c was never in the domain to begin with. Whereas when you start thinking about calculus and start thinking about limits, you need to train your brain to think about approaching, right? I'm approaching, I'm getting close. And that's totally different than just standing in one spot, right? I know that the door to this room is over there, so I have to approach it. But not until I actually, sorry, you can't see the doorway, but not until I'm actually standing in the doorway can I say, I am in the doorway. I could approach the doorway and then all of a sudden, there's no doorway there. A hurricane comes by and wipes it away. I was still approaching the doorway, whether it's there or not, doesn't really matter in terms of limits. That's kind of a bad example. Hopefully no hurricanes, right? Knock on drywall. So this is our, again, sort of intuitive, or the book uses the word intuitive definition of a limit, right? We're limited to this value by approaching this number c. Later on, we'll get a bit more rigorous of a definition where we get to put some bounds on the actual output values and some bounds on the input values, and it really locks us into, yes, this has to be the limit, because we can squeeze things infinitesimally close together. Okay, so with that initial, nice definition under our belt, let's see if we can get a couple of examples here. For instance, the first one, I'm just going to start off with a nice linear function. Find and again, we'll practice saying this, find the limit as x goes to 2 of 2x minus 1. And you'll notice I'm putting parentheses around this linear function 2x minus 1. And that's just notation stuff to keep aware of. If I do it like this without parentheses, it could be confusing. I might be saying, hey, find the limit as x goes to 2 of 2x, and then later subtract 1. Like if I wrote it out like this. Right, that might be a bit more confusing. Hey, Mr. Schaller, am I only finding this limit and then subtracting 1? Well, to be very clear, we use parentheses to say, no, you're finding the limit of this entire linear function. I'll make that 1 a little better. So again, notation-wise, if you have multiple terms, you put all those terms you want inside the limit, you want those in parentheses. Or brackets. Maybe I've seen people use brackets before as well. So let's see. What I'm going to do is first graph the function. Now it doesn't say to graph it, but it'll be nice to see what's happening. 1, 2, 3. We're only going to x equals 2, so I don't have to go out very far. 1, 2, 3, 4. 1, 2, 3, 4. Maybe I'll squeak one more in there, just to square things up. So we're concerned about x getting close to 2, but not exactly on 2. So we've got a slope of 2, and we pass through -1 on the y-axis. Up 2 over 1, up 2, and we can still squeeze that in up there, and we'll draw. And it's a linear function, so it's just a straight line. Maybe this isn't the best straight line in the world, but there it is. So what do you think our limit is? Right, as x goes to 2, where do you think this L is eventually going to land? Again, it's a linear function, so it's not like we're going to be approaching, nope, or approaching, nope, just kidding. It's a straight line. So no matter what, we're locked into, if we go close to 2, our range, our output values are getting closer and closer to 3. So we would say that L is 3. Well, maybe we don't have the most confidence right now to declare that. We should. It's a linear function. I'm picking a cheap example here. Let's get close to 2. Let's start at maybe like 1.5 and see where we land. Right, if I start by getting close to it I'll just start from the left-hand side and see where we go. If I plug in 1.5 and then double it, I get 3 minus 1, which is 2. So here's an input, and here's an output. Well, let's get a little closer. Let's plug in 1.9. And I already went ahead and did some of these on a piece of paper just to speed things up. I get 2.8. Let's get even closer. Let's go to 1.99 and see how close we get to this L. And we do. We get 2.98. But that's just from one side. Who's to say that when we get to 2, we're not up at some value 100? I mean, clearly we're not. We know linear functions very well. But again, just to show it numerically. And when they talk about things like numerical analysis, this is a lot of what you're doing. You're just plugging in lots of numbers and seeing what you get as far as results. So let's start a little distance away at 2.5. Again, I'll emphasize we're trying to get to x equals 2 to get this L of 3. Well, if we plug in 2.5 into our function, we get 4. If we get a little closer, say like 2.1, that's a little bit bigger than 2, but it's very close to 2, we get 3.2. If we plug in 2.01, that is very close to the number 2, we get 3.02. So you'll notice that in both cases, I'm getting closer to 2, closer to 2, closer to 2, and I'm also getting closer to 3, right? It looks like eventually I'll get to the value 3. And then as I come in from the right and get closer to 2, 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 I keep zooming in on this input of 2. That keeps me zoomed into this output of 3, right? Eventually this thing is, as I get closer to the input 2, I get closer to the output 3. So again, it's about approaching, right? But you'll notice that, hey, wait, can't I just plug in 2? 2 times 2 is 4, minus 1 is 3. Can't I just find the limit pretty easily by saying the limit as x goes to 2 of 2x minus 1 must be the same as 2 times 2 minus 1, which is 4 minus 1, which is 3. And I'm not going to tell you you're wrong. You're absolutely right. And in fact, stuff like this does work, but we don't have the tools for that yet. Because what if, and this is where problems finished, we found it graphically, we found it numerically, doing some approximations. And one of the ways that I did it, I apologize, I don't have the software in my calculator But if you do have one of these nice TI 83 or 84s, you can input the function 2x minus 1 and then hit your second table and plug in some of those input x values. These aren't the ones, these are a little different. But you can plug in these input x values and it'll just spit out those output y values for you. So it's not like you have to do this by hand. I didn't do it by hand. I used the table setting in my calculator, which you should be comfortable with now. College algebra, you used it. Trig, you used it. Pre-calc, you used it. So you should be comfortable with your calculator by now. If you do need some more help on the calculator, I'll see what I can do. I'll see if I can get the app so that I can pull the app up on the screen. But for the most part, we're not going to need it. We're not going to need to rely on it too heavily. I might just be able to show you a quick thing on the screen and then take it away. Okay, so we've got like a bunch of different ways we can show this so that we're confident that the limit must be 3. Graphically, numerically, and then this, we're kind of jumping the gun a little bit here. The reason we can do this, the reason we can just plug in the value 2 is because this is a smooth, continuous function whose domain is all real numbers. I just said a mouthful. I mean a giant mouthful. Smooth, continuous, domain, all real numbers, right? That thing had to fit a very precise group of functions in order for me to do this. Problem solved, limits 3. I should just shut up about it, but watch what happens if there's a hole. Oh, I meant to get rid of the green. But watch what happens if I put a hole in the function there. And I'm emphasizing there's a big hole in the function. Really, it's just that one infinitesimal point. What if I say that I'm going to take this linear function and restrict it so that 2 is no longer in the domain? Every other number is fine, just 2. You are not allowed to use 2 in this linear function because I said so and I'm always right. No, that's not true. But let's say in this case, 2 is not in the domain. Would I have to get rid of the limit? No, because I'm still approaching the limit 3 from the left and from the right. These numbers would still be getting me closer to 3 from the left, and as I come in from the right side of 2, I would still be getting closer to the value 3. A limit doesn't care about the number 2. It wants to approach the number 2. But if I talk about the value at x equals 2, well, that does not exist because there's a hole in the graph. Big difference between a value, you only care about that point, versus a limit. You only care about approaching. Right? So that wouldn't change anything. It would still be 3 all around. Right? But that's where this would fail. If this was a hole in the graph, I couldn't plug that in because this function is not defined when x is 2. Now I lose this strategy altogether. Again, we're jumping the gun. But I want to show you the difference between a limit approaches and doesn't necessarily care about that value so much versus actual just plug in this x value, get out a y value. Big difference there. Big difference that we need to be able to differentiate between what this word limit really means and what is just some value. So let's take a look at another example where let's say we want to find the limit as x goes to 1 of x minus 1 over x squared minus 1. Now I know what some of you are thinking. You're thinking, oh, well, I'm not going to graph it, and I'm not going to sit there and play with my calculator. I'm just going to plug in 1. Well, watch what happens, right? This is what I would like to call a bad strategy, which means don't do that. I'm going to say, oh, well, the limit as x goes to 1 of x minus 1 over x squared minus 1 must be just 1 minus 1 over 1 squared minus 1, which is 0 over 0, which is, I have no idea. This is not 0. You cannot divide by 0. This is not infinity. This is not 1, right? Same thing over same thing. This is not 17 pi. This has no meaning. In fact, we'll see a little bit later, we give this a very specific name. We call it an indeterminate form. You cannot determine what that means. And you're thinking, oh, okay, well then this function just doesn't have a limit at x equals 1. Well, look what we can do. This is what I like to call a good strategy. We know that from pre-calculus, we can simplify some of these rational functions. So I'm going to say let y, or maybe I should just say f of x. Let's do that. Let f of x equal this function that we're trying to find the limit for. Right. Let f of x be this guy, so that we're looking for the limit as x goes to 1 of f of x. I'm just generalizing the function into a generic f of x. Well, then f of x is the same thing as x minus 1 over x plus 1 times x minus 1. I hope you all know how to factor the difference of squares still. That's all I'm doing in the denominator. X squared minus 1 squared, that's x squared minus 1. That is the difference of squares. And my favorite word in mathematics, cancel, cancel. So f of x is x minus 1 over x plus 1 quantity times x minus 1 quantity, which means f of x is equal to 1 over x plus 1. And now we're going back to actually college algebra, essentially. And we're looking at this shift. This is a rational function. Looks like that toolkit function y equals 1 over x, but it's just been shifted, and with the plus 1 down here, it's been shifted to the left 1 unit, which means my function looks like this. There's negative 1, there's 1, there's 2, there's negative 2. We don't have to go too far with this. I want to emphasize that x cannot be negative 1. That is what we call a vertical asymptote, because we would be doing 1 divided by 0, which we can't do. And then our function just kind of rides along the x-axis till it gets close to that vertical asymptote, goes down to negative infinity. There is nothing at the asymptote. I want to emphasize that. And then on the other side of the vertical asymptote, it shoots down from positive infinity and then eventually rides along to 0. That is our horizontal asymptote. And again, if you need a little refresher on horizontal asymptotes, right, there are different cases. This is the case where the degree of the top, the numerator, is less than the degree of the bottom, the denominator, meaning our horizontal asymptote must be y equals 0. Wow, notice how all this stuff is all coming into the big picture, right? We didn't just learn pre-calc to forget about pre-calc and learn trig to forget about trig and then go, oh, now I'm going to learn this new subject, calculus. We're just building on everything, right? So we're using all that stuff that we've had before to visualize this. Now what happens as x goes to 1? We wanted to find the limit as x goes to 1 of this function, which is essentially the same thing as this function once I simplify it, and I can plug 1 into this function. In fact, when I plug 1 into this function, I get an output of 1/2. So what I'm looking at is finding the limit as x goes to 1 of x minus 1 over x squared minus 1 is equal to the limit as x goes to 1 of 1 over x plus 1 when I simplify, which is 1 over. Now all of a sudden I'm allowed to plug in 1 and get a half out of it. And again, I'm doing this sort of visually checking. You can graph it on your calculator, do it that way. You can make a whole XY chart. And before even doing this simplifying, you can make a chart and numerically analyze this by coming in a little from the left, say like 0.9 and then 0.99 and then 0.999. and see where you end up getting. Eventually you'll get close to a half the closer you get to 1. And analogously, from the right-hand side, you can start with 1.1, 1.01, 1.001, right? You can keep getting closer and closer. Same thing eventually getting to this L value of 1/2. So that gives us our limit. Now, here's a thing where I still have this x cannot equal -1, but we're at +1, and the function is defined there, which is totally fine. But again, I just want to emphasize, if there was a hole in the graph there, if I told you x can't be 1 in the domain of the function, and there was a hole there, you would still have to tell me that the limit is 1/2. But you sort of lose this ability to plug in 1, because I removed 1 from the domain. So you can see that limits have this sort of this extra little cushion, so that if there's a hole there, the limit doesn't get affected, because you're only talking about getting close. By only affecting that one infinitesimal point, you don't affect the terminology of getting close, right? Because you're not at the point, you're just close to the point. So I'm really trying to drive that home. That seems to be the number one thing when it comes to limits. Students, they have a hard time breaking away from algebra, where it is I plug in a value, I get out a value. That's very just 1-2. Whereas limits are not like that. Limits talk about approaching. There's all this space that you have to consider around that point. Whereas with the algebra, you just plugged it in, right? You weren't concerned about what was next to the value you're plugging in or the value you're getting out. Now you have to be concerned about what's next to, what's close to, what's in the neighborhood of. Maybe there's a little neighborhood around the point, and you have to be concerned about everything around that little neighborhood. And you'll hear me use the word neighborhood again when we get to the more rigorous definition. Yes, the word neighborhood has a very specific meaning in mathematics. Okay, let's take a look at another one. This one I want to steal just right from the book, and it is essentially the limit as x goes to 0. Of sine of x over x. There's that trig. Right? So, and this is not sinks. This is sine of x. That's our function. Well, sine of x divided by x is our function. And again, right off the bat, before I even attempt anything strategy-wise, there's no simplifying this. And please, sine of x divided by x, cancel. That's a sin. Please don't do this. Right? There's a very specific reason I really like to use lots of parentheses around things. This is what we call the argument of the function, and this is just the variable x. They have completely different meanings. Right? And you also see silly things like this when you do natural log of x over x. That is not natural log, because what is the argument? What is the argument? Right? You're giving me nothing at that point. You're basically saying, I don't know how to handle a sine function, or I don't know how to handle a log function. Break those bad habits immediately, right? Even on the first test, that's going to look really, really bad. Obviously, maybe it's been a while since you've done some algebra or some trig. The first exam I might be a little lenient, but if you're still doing this on exam 4 or on the final exam, you do not pass Go. You do not get to take Calc 2, because again, it's a language, and you're just abusing the language at that point. So this is bad. Don't do stuff like this, right? Don't be canceling out an argument with a variable. So x can't be 0, because that x is stuck there forever. It's in the denominator forever. So I cannot plug 0 into that function, sine of x divided by x. Right? That is a very important thing. But notice what I'm looking for. I want x to go to 0. I'm trying to let x go to 0, but x cannot be 0. So there's inherently just a problem there. So first I'm going to do it graphically. I guess I'll have to, no, you know what, I'm not going to erase those. I'm actually just going to block them out. So I'm going to do this in graphically. I'm just going to go to the calculator, and I'm going to type in sine of x divided by x. You know, not the limit stuff, just sine of x divided by x. So there is one nice way to do it. I hope that's shown up. There we go. And then I'm just going to go to my basic graph. And if you ever, if your graph ever looks off, or it's stretched weird, or it's not centered, I always like to hit this button zoom in the middle, and then go down to number 6. Just hit the number 6, zoom standard. Always reset your window back to the very basic window. You just get a little visual on the function, but we're concerned about x going to 0, so I'm going to zoom in, which is number 2, and I'm going to pick where I want to zoom in. It looks like it's kind of a little above the x-axis when x is 0, so I'm going to move that cursor up a little bit. It lets me choose where I want to zoom in, and then I'll hit enter. Now, notice the calculator just makes a nice, smooth, and continuous curve, and it's telling me my output right now. If I look at it, well, let's go to table, second table. If I look at this and I plug in, I'm going to type in the number 0 and hit enter. See how it says error? It knows x can't be 0, so it can't give you an output. But if I go to my graph, again, sorry for holding the calculator up to the screen, but hopefully it's getting the point across. The graph looks smooth and continuous and perfectly fine. So I'm going to draw it, and it's not going to be the best drawing, but it's just going to be a sketch where it kind of does one of these numbers, right? And this is the output value 1 when x is equal to 0. Here's y equals 1. The problem is x can't be 0. There's a hole there, right? 0 is not in the domain of that sine x over x function. But the calculator is drawing it just fine, because the more you zoom into that hole, it's going to fill in. And then you zoom into that hole on the calculator, it's going to try and fill it in. And then you zoom in some more on the hole, it fills it in more, because it keeps having more resolution to play with. So do be careful about when you graph things on your calculator. It is not the most ultimate revealing thing, but you'll notice if you check on the table, you'll see what happens. And again, you can go to your x, y values. Give myself a little more space there. And just to do a couple, you can come in from the left, right? You could start at, say, oh, I don't know, maybe negative 1/2, right? You do negative 0.5, negative 0.25, negative 0.1, right? You're getting closer and closer to 0. And you can put those into your calculator. And I do want to mention this, just in case you haven't done this since Trigger Pre-Calc, or maybe you've changed your settings. If you go to, on the calculator, hit the second button, and then hit Window, which actually highlights the blue table set. This is what your values should look like. Scroll down so that the independent variable is on ask. That means the calculator is asking, okay, what x value do you want me to plug in? And make sure the dependent variable is on auto, because that will tell you the output, the y value. And then go to second table. And I'm going to plug those values in. Negative 0.5 and hit enter. Negative 0.25, I'm getting closer to 0, enter. Negative 0.1, enter. Notice how those values, 9.5 something, 9.8 something, 0.95 something, 0.98 something, 0.99 something. Eventually, as I get closer and closer to 0, it's going to start giving me an error. Like if I did negative 0.0000000001. That is shockingly close to the number 0. And notice it's telling me the output is 1, right? So the calculator starts to say, all right, I don't have that much accuracy, so I'm just going to give you what I think it is. Or if I do negative 0.00000000, I'll see how close I can get with how many zeros it'll allow me to get away with. There we go. And then I'll put a 1 in. That number is basically 0 in the grand scheme of things. And the calculator says, yeah, it's still 1. So again, the calculator can only be so accurate, but eventually this function is going to the value of 1. But notice this is never, x equals 0 is never in the domain of this function, but I still get to say that the limit as x goes to 0 of sine x over x is exactly 1. There is no amount of trickery of cancel, I'll plug in 0 that could ever work on this function. But graphically or numerically, I didn't really copy down the 0.95, 0.98, 0.99. We will do that now. And forgive my rounding here. The rounding might be a little off. But again, eventually from the left, you're seeing that you're getting close to 0.99. And you can do the same analysis from the right to make sure. And ultimately, you do want to make sure by looking at the other side, just to make sure, again, that these are going to the same place. Because we will encounter functions that kind of diverge when you get to some sort of like vertical asymptote. They might, shoot like down to negative infinity, and one's coming from positive infinity. In that case, you do not want to run the risk of only evaluating one side. Right? You always want to make sure that on the other side we have some agreement. So back to the calculator, I'm just going to do 0.5, enter, 0.25, enter, and 0.1, enter, and you can see they agree. Right? You can see they're also in agreement for the positive values, which are a little bit further down here. So those agree. In the sake of saving time, it's the same thing, just with the positive stuff. So again, really try and have that disconnect between what is the value that I plug in and get out versus what is a limit. When I see this limit notation, I know that I need to do a little bit different work. I can't just plug in the number it's telling me to plug in. Right? When it says let x go to 0, you can't jump to the conclusion of, all right, x is 0. Well, no, it's not. It's going to 0. That's an entire process. You don't just want to skip that entire process and make it 0. Right? That's not what we're saying. So don't jump to conclusions. That's that. So you can see that I'm coming from the left and from the right, and that is what we call one-sided limits. So what we can do is essentially just say, well, what is the limit from one side? Right? I'm looking at it from both sides to make sure I get the correct L. But what if I don't care about the other side? What if I just want to come from the left and see where the function goes? What if I want to just come from the right and see where the function goes as I get close to a value? That means I don't care about that stuff over there. I'm only coming in from the right-hand side. I don't care about left-hand side stuff. So that's where you can see some funny things happen. So what I want to do is kind of start off with like a motivating example, and this is a pretty popular function known as the Heaviside function with 2 i's in it. Heaviside was a man, that's why it's capitalized. Heaviside was, I believe, an electrical engineer. Maybe double check my facts. Type in Heaviside, I forget his first name. But I think he was an electrical engineer that came off with this function, and essentially what it does is it mimics like a light switch. It's off, its state is 0, it's on, it stays 1. And there's a specific time that happens when it goes from off to on. Right? So that's why he kind of came up with this, or he's popular for this function. And you'll see why in just a second. So the Heaviside function is defined by what we call a piecewise function. Should remember these from college algebra and maybe a little bit also in pre-calc and trig. And that function is capital H of t. They use t instead of x, t for time, essentially. And this is how we draw a piecewise function, right? 0 if x is less than 0, and 1 is the output if x is greater than or equal to 0. And let's draw this function. So what's happening with the piecewise function is you get this output when your values are less than 0, i.e. negative. And when your values are positive or also 0, right, greater than or equal to 0, then you use this output positive 1, which is just a constant positive 1. So I will draw this Heaviside function in blue. I'm always going to get the output 0, which is a constant, all the way up until t is 0. So this is technically my t-axis, and this is h of t. And then I will get the output of 1 for anything greater than, oh, I'm sorry, I put x there. That might be a little confusing. Let me fix that. I knew something was a little off. I just couldn't pinpoint it. Those shouldn't be x's. Those should be t's. Right? T's everywhere. that is the value 1. Now I guess we'll put a 2 there, we'll put a negative 1 there, negative 2, just so everything has a little bit of a scale. You don't have to go this crazy, put all those values in there. But that's what the function looks like essentially. And yeah, it keeps on going forever, right? Because t can keep on going forever. And same thing, we look more towards the negative values for t. It keeps on going forever. So I'll put some arrows there. So this is our Heaviside function. Basically the easiest piecewise function we could ever come across. And let's say we want to find the limit as t goes to 0 from the left of h of t. Well, we'll start with that. Notice this little notation here, this little negative sign. It looks like it's 0 to the negative power. I don't know if that's coming across. Yeah, that's pretty good on the screen. It looks like the limit as t goes to 0 raised to the negative sign. Well, that's not how we say that. The way we say this is the limit as t goes to 0 from the left. All right, so we say the limit as t goes to 0 from the left of h of t. So when you see this little negative, it looks like that negative is in the power of that number. That's how we say that. We're looking at the limit from the left. Naturally, because negative numbers are on the left of our Cartesian coordinates here. Well, again, since we have the picture, we can do it by plugging it into the calculator. But we would only use values like -1, -0.5, -0.2, -0.1, -0.01, and we would never care about coming from the right-hand side. We would only care about coming from the left-hand side. So essentially, I'm going to grab a little piece of paper to kind of emphasize this. We don't care about that stuff over there. This is all we care about, from the left. So we care about coming in from the left and approaching, and getting really, really close to t equals 0. Well, it looks like I'm getting the output of 0, right? And I know there's a hole there, but it looks like I'm getting an output of 0 because really that hole isn't that large, it's infinitesimally small. So I can keep getting closer, and I keep staying towards this value of 0. So as I approach, coming in from the left, I still get an output of 0 because I'm only looking at negative values, therefore I must be sticking with this output of 0. Thus, the limit as t goes to 0 from the left of h of t, and I'm simply writing h of t here so I don't have to rewrite the entire piecewise function, must be exactly 0. And now we'll use the right-hand side limit, where we'll say find the limit as t goes to 0 from the right of h of t. Again, by looking at it from the right, you'll notice that there's this little positive. And it looks like it's t goes to 0 to the positive. What that means is it's just the notation that this little plus here, 0 to the plus. The way we really read that is the limit as t goes, variable t there, as t goes to 0 from the right. Of h of t. All right, so we want to find the limit as t goes to 0 from the right of our Heaviside function h of t. So that's how we would say that. We'd have to throw that extra little from the right in there. Now, again, let me steal my piece of paper here. We do not care about this side at all. Here's t equals 0, it's right there at the origin, and I only care about coming in from the right, closer and 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 closer, as close as I ever want to get to the actual number 0, but never actually being 0. Again, we can do it numerically on the table on our calculator, or graphically, we can see it here. Any positive number and 0 itself, greater than or equal to 0, is always going to try and spit out this value 1, which means the limit, as I approach from the right, is going to try and approach this value of 1. So thus, the limit, as t goes to 0 from the right, of h of t must be 1. Now, okay, we've got the picture, and we know what we're trying to find as far as, like, you know, part A of the example, part B of the example. I'm going to erase the top a little bit, but keep this function in mind. So we're still using the same function, but I just want to squeeze in a part C to this example. All right, so we've got part A, we've got part B. Let's take a look at part C, which might ask us to find the limit as t goes to 0 of h of t. Now be careful with this. This was approaching from the left. We wanted to come in from the left and see where we eventually got. Well, we didn't really go anywhere because we never lifted off that x-axis. We always stuck with 0. And then this asks for part B, find the limit as t goes to 0 from the right of this Heaviside function. Well, we never lifted off this constant 1. In fact, even if we were to be at 0, we would still say 1 based on the Heaviside function. But what happens if we look for the limit as t goes to 0 of h of t? In this case, the limit as t goes to 0 of h of t, you might have a guess already. Maybe you already guessed. Does not exist. Maybe you had a good guess, maybe not, but a guess is still closer than nothing at all. Sometimes we abbreviate this does not exist as DNE, and I'm perfectly fine with that. You'll see that in the textbook as well. We'll say, you know, the limit as t goes to 0 of h of t DNE, and they use a capital DNE to say does not exist, which is perfectly fine. Whoa, 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 what's this? Now you're throwing more new stuff at us? So go back to the definition of a limit. Right? As I get arbitrarily close, I can make this thing approach L. Approach one number, that number must be capital L. So rewind or go back to your notes, right? Look at the definition of a limit. It has to approach this number, capital L. Now, as I get closer and closer and closer from the left and from the right, am I approaching a number L? No. From the left, I'm getting close to 0. From the right, I'm getting close to 1. There are an infinite number of numbers between there. All right? There are an infinite number of real numbers between the number 0 and the number 1. How do I know which one is my capital L? And I can't just choose one because it's on that side, because then I'm ignoring the other side. This is talking about a general limit. It is approaching 0, which means you have to think about from the left and from the right at the same time. For those of you who are going to take Calculus 3, that's when you start dealing with some three-dimensional stuff. You'll have an x, y, and a z-axis. Well, the x-axis goes in and out when you draw it. You'll have 3 axes that you have to account for. That means you can approach from an infinite number of directions. Right? There's a whole bunch of directions you can approach. Whereas here we're only two-dimensional, so when we talk about this input t, we're either coming from the left or from the right. We're not coming from up or down because that deals with the range, that deals with outputs. Inputs are either on the left of something or on the right of something. So for Calc 1, it's not too hard to look at limits because you're only looking for two sides. So if we want to find a general limit, then I need to pinpoint exactly what this capital L is, and that's the problem. This L is the thing that does not exist. I can't say that the limit's 1 because from the left it's 0. I can't say that the limit is 0 because from the right it's 1. I can't say that the limit is a half. Why am I taking an average, right? So that's one thing that we do have to be careful about. Sometimes limits cannot exist. But what about at 0? if I plug 0 into this function, the Heaviside function, when I plug 0 in, it is defined to be 1 as the output. So now it's kind of the opposite of what we saw in the previous examples, where maybe the actual function itself doesn't exist there, but the limit still works because of the hole. Now we're seeing the opposite, where in this case the function is defined there, but the limit doesn't work because there's this like jump discontinuity. Ooh, I just said a very fancy word, discontinuity. In fact, a little more fancier when you combine jump discontinuity. It's a very specific type of discontinuity. That could be an issue. Maybe continuity. Maybe we need things to be, like I said, smooth and continuous. Not a bunch of jagged breaks and jumps. Not a bunch of vertical asymptotes cutting things off. Right? So we want to deal with nice functions, and that's the reason we call them nice functions, is because generally in that sense we can just plug something into the function because it's got a nice domain. But these functions are not nice, right? They jump all around, especially when you start working with piecewise functions. Those things can be a mess. And of course, we've also got examples as far as trig functions, right? Trigonometric functions. Those things are cyclical, which means that they kind of like repeat themselves. Some of them are very nice. Look at y equals sine of x, right? It's a very nice function. Just oscillates back and forth between -1 and +1. But then you look at something like secant of x. Oh, so an infinite number of vertical asymptotes. So that could be a really nasty function to deal with. So this lets us summarize things up. And I try not to let this lecture go too much longer. I just want to kind of summarize things up and then maybe hit like 2 more examples. So here, now, when I mention a theorem, as far as in calculus, when I mention a theorem, I'll never force you to prove it because you really need to practice writing proofs before someone says, hey, prove this. If you've never proved something before, it's almost near impossible to do without knowing how to construct a proof. I may prove some things if I feel like they really deserve the proof. But for the most part, when I mention a theorem, boy, that better be in your notes. That better be written down. And I don't mean just, oh, I watched the video, I remember the theorem. Oh, that's not how that's going to work. By the time you get 3 or 4 chapters in, you can't remember stuff like that. You need it written down somewhere on some notes, concise, call it a cheat sheet, if you will. Right? So whenever you see the word theorem, you should be thinking, I have to know this because this is how I solve this problem. Right? So this is I guess basically what our first theorem is going to be. And that is the limit. And I'm just going to make it nice and short and sweet. As x goes to c of f of x equals L, that means that this limit exists if and only if the limit as x goes to c from the left of f of x is equal to L, and this is a very important and, the limit as x goes to c from the right of f of x is equal to L. Now, when you look at criteria like this is what we call an if and only if statement. This is an if and only if statement. And that is very important because it's a lot more powerful than saying, well, this happens only if this happens. That's a one-way street. This has to happen first, and then that second thing can happen. Or there's if statements. Yeah, this thing could happen if this happens first. It's like saying a similar thing, but saying it backwards. Your first criteria is actually the end of the sentence. Right? That's saying you don't get this until this thing is satisfied. Right? So those are one-way streets. But an if and only if statement is a two-way street. If we have that the limit as x goes to c of f of x is L, then we automatically know that this has to follow. The limit from the left and the limit from the right also exist and also equal capital L. That's a one-way street going this way. Or we could say it backwards. Hey, I found the limit as x goes to c from the left to be this number, and I found the limit as x goes to c from the right be the exact same number. This is an L and this is an M, right? These aren't two different letters, these are the same L. So these have to match. Oh, well, if they match, it doesn't matter that there's a hole there or it's filled in there or the point that should be there is up here or down here. It does not matter. I found the left and the right limits to be the same. Then that means that the limit exists and it must also be that letter or number L. So the nice thing about these if and only if statements, they are like a two-way street. Those are very powerful statements in math because knowing part one gives me part two automatically with zero effort. Or knowing part two gives me part one automatically with zero effort. Whereas if it's only a one-way street, then you run into situations where you might make a poor assumption of, well, I have number two because of number one. Well, if it's not specifically stated that way, then that's not true. Or, oh, I know this because I have this. Well, that might not be specifically true if it's only a one-way street, if it's only an only-if statement, or if it's if this happens, right? That's if this, then that. There's a first part, then a very specific second part. Just because you have the second part does not mean you have the first part, right? You're making an assumption there. But this is fine. The if and only if statement is fine. So when you're working on some of these exercises in the book, if it asks you to find the limit, you may have to break it down to finding the left limit and the right limit, showing that they're equal, and then concluding that there's your limit. So if it asks you for this, this is probably the path they might need to take. Or if it asks for a left and a right limit, and you find a limit, then you can say, okay, well, this is the limit of the function, because it's either like smooth and continuous, and I can see it on the graph, or I did my numerical analysis, right? I found the left and the right by breaking it down into pieces. Maybe you can find the limit and then infer, because this is a two-way street, that this has to also happen, right? So if they're asking for a left and a right limit, they're being very specific about which side. But if they're asking for the full-blown limit, you really need to check both sides. Right? We will come across situations where we see graphs of functions that have this vertical asymptote and they might not go to the actual same value L. Well, then we'll have to conclude that the limit does not exist because these don't match. And that's why I underline this word and. Right? So if you find the left-hand limit and then tell me the limit, you may not be correct because these might not be the same. This has to be L and this has to be L. If this is, say the limit's 3 and this limit is -3, then you don't get to conclude that the limit is 3 or -3, right? So they don't match, they don't make sense. So this is a very powerful theorem when it comes to limits. And we're getting it before we even really talk about the rigorous definition of a limit. So, okay, like I said, a couple more examples to really drive this home. And then that should wrap up this section. And I kind of want to do this a little bit more graphically by first drawing, that black marker's kind of drying out a little bit. First I just want to draw a function. Place some values down here. Let's do 1, 2, 3, and we'll put a 4, -1, -2, -3 is good enough. I don't have the space to go further. Same thing here, 1, 2, 3, 4, -1, -2, -3, -4. Those are both -1. And I just want to draw a function. Bear with me here because I'm just going to kind of do it off the top of my head. Ooh, a little bit of thunder there. I wonder if you heard that. Let's say we put a hole there, and then that filled in 3. We'll do another hole there. That's good. We really want to not go too crazy with this stuff. So I'll give you some specific points here. At 0, I'm crossing through 3. I want to be clear about that. At 1, I'm crossing through 1. There's a hole there. I want to be specific about that. And then, I wanted to connect this as well. Let me connect that. Right, 2, there's a hole, but then I jump up to 3. And at 3, I'm crossing through 1. And then what I want to do is just basically look at a graph like this and see how many limits I can find just based on what's happening with the graph. So let's say we want to look at the limit as, and this is the x-axis, by the way, this is the y-axis, as x goes to, well, let's not call it y, let's call it f of x. Let's say we want to look at the limit as x goes to 0 of f of x. Let's say we want to look at the limit as x goes to 1 of f of x. Let's say we want to look at the limit as x goes to 2 of f of x. And let's say we want to look at the limit as x goes to 3 of f of x. So that's kind of why I wanted to put some important points down. When x is 0, for my first part, that's pretty straightforward. When I look at this from the left and from the right, I am approaching this capital L value of 3. Again, notice how I'm looking from the left and from the right, because that implies the first part of the theorem, that the limit as x goes to 0 of f of x must be 3. And there's a very specific reasoning for that, and that is because, and I won't do this for everyone, but I'm not going to do this for each one. I'm just going to say because the left and right limits exist and are both 3. So if you look at a theorem, it's like reading it backwards, right? It's an if and only if statement, but I'm getting the second part. The left and the right limit are both 3. The left limit is 3 and the right limit is 3. Therefore, I can conclude the first part of the theorem. Because if this happens, then that happens, and also if that happens, then this first thing happens. So I'm using it backwards. If that thing happens, well, it did happen. Thus, the first thing must also happen. The limit as x goes to 1 of f of x, do I care that there's a hole there? No, I don't. From the left, I can get as close as I want, and I keep getting closer to this output value of 1. And it doesn't matter how steep I'm coming down into it. I'm coming very, very, very steep down into this output value of 1, but I'm still going to the output value of 1. And from the right-hand side, again, I'm not as steep, but I'm approaching this value of 1 where this hole is, which means I'm approaching a limit of 1. Why can I say that? Well, because dot, 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 the left and the right limits exist and are both dot, 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 positive 1. Right? So I get to say this because of the exact same reasoning. But there, I wrote the 3, sorry, I meant the 1. Right, the left-hand limit is 1, the right-hand limit is 1. Therefore, I can conclude that the limit itself must also be 1, because they match up. Now, what about the limit as x goes to 2? And again, you probably have a good guess for this already. Does not exist. I'm just going to write DNE for short. And you're thinking, well, wait a minute, the left-hand limit is approaching this value of 0, right? It's coming to the x-axis from the left. As I approach closer and closer and closer, I get to this constant 0 eventually. But as I approach from the right, I get to this value, 3. Whoa, those guys are way off. That's not the same L. L can't be in 2 places at the same time, and there's an infinite number of choices between those 2 choices. So from the left and from the right, I'm going 2 different directions. That's like someone giving you 2 different directions. Saying, hey, you want to meet me in Tampa? Drive north. Oh, you also want to meet me in Tampa? Drive south. right? And then you're going to start to like split here. So I could be somewhere in the middle and be sending you in two different directions, which means this limit is not going to agree. Notice I'm failing the theorem. This limit is L, capital L, which means it exists and is some number, if and only if the left and right limit are the same. This does not exist because the left limit is 0 and the right limit, or a lot of people like to say left hand limit or right hand limit. I'm just squeezing it in here because I don't really have the space. The left limit is 0 and the right limit is 3. Again, I'm approaching 2, but I'm never actually being 2, so the best I can tell is that I'm going up to 3. Those do not agree, therefore I cannot say anything about the limit. And of course the last one here, part D, what is the limit as x goes to 3 of f of x? I'm going to be real cheap with this one. It's got to be 1. As I get closer and closer from the left, I'm going to use my very high-tech visual aid here, a piece of paper. As I get closer and closer to 3, look what output I'm going to, right? I'm approaching 1 from the left. Same thing on the right-hand side, very high-tech visual aid, piece of paper helping me out here. I'm approaching. I'm never actually getting to the value 3 to plug it in, but I'm seeing where I'm going, and I am going to the value of 1. So the left and the right limits agree. That means my limit must agree with those left and right limits. Even if there was a hole there, I would still say it's 1, right? Because the left and the right limit agree. Okay, and then one last thing to get this all wrapped up. Let me see. Yeah, we're at an hour and 17 minutes. I'm going to try and keep these lectures, each section to, oh, I already have problems there. That's okay, you got them. I'm going to try and keep each lecture to, hopefully, at least definitely under an hour and a half. But this one's a little long. There's quite a bit of stuff to cover in here. So what I want to look at now is just bringing something back into the picture from college algebra or pre-calculus, and then we'll be done. We'll wrap this up. The vertical line, x equals a, is called a vertical asymptote. And we'll refresh on horizontal asymptotes in a later section. But right now we will call this a vertical asymptote if one of the following is true. Notice only one of the following actually has to be true in order for this to work. The limit as x goes to a of f of x is infinity. The limit as x goes to a of f of x is negative infinity. The limit as x goes to a from the left of f of x is infinity. The limit as x goes to a from the left of f of x is negative infinity. The limit as x goes to a from the right now of f of x is infinity. And last but not least, it could be such that the limit as x goes to a from the right of f of x is negative infinity. Right, so if any one of these situations happens, we call that a vertical asymptote. It's just a way of redefining something we've already learned. We know what a vertical asymptote is. All right, so let's take, for example, I'm going to say let y equal x squared. Or sorry, not x squared, 1 over x squared. I need an asymptote here. If we draw this function, it looks like this. I'll do it in blue. And again, I'm not being very specific about x and y values, except that right here at the origin, obviously x is 0. And x can't be 0 in our function. 0 is not in the domain of the function y equals 1 over x squared. All right, so that is our vertical asymptote, or I like to abbreviate it VA for short. So that's where we have a vertical asymptote. We can't input anything into the function here, and this isn't like a hole in the graph or anything, I just wanted to show you that's where x equals 0. We can't input anything into the function because we get 1 divided by 0, which is nonsense. It's not a number, so we can't make any sense out of it. So what we can say is, if we look for the limit as x goes to 0, from the left, I'm putting a little negative thing right there, of 1 over x squared. Notice where it goes, it shoots up to infinity. So this limit can be as large as it wants to be. As I get closer to 0, my values go insanely huge. But I'm never at 0, right? That's the thing about a limit. I don't use the number 0. I just get as close as I want to 0. And when you say, hey, I want to be closer, you can always get closer and closer and closer and closer. You ever play that game with your brother or your sister where you say, look, I'm not touching, I'm not touching, I'm not touching, but you're annoying the crap out of them because you're getting too close? Same thing here. We're getting way too close and annoying the crap out of this number 0, but we're never actually touching it, so we're never running into this issue where x can't be 0. Likewise, on the other side, the limit as x goes to 0 from the right, I'm putting a little plus up here to say this limit is a right-hand side limit of 1 over x squared, must also be infinity. Right? That thing can be as large as it wants. And then you're thinking, okay, both of these limits are infinity, so the limit as x goes to 0 of 1 over x squared, since the left-hand limit and the right-hand limit exist, and they're both the same number L, then this must be the limit. Yes and no. Short answer, yeah, okay, but infinity is not a number. I want you to keep this in mind. Right? Note, infinity is not a number. It's not some finite number. It doesn't behave the same way as numbers do. 2 is less than 3. They're well ordered. 3 is greater than 2. They're well ordered. Negative integers are always less than positive integers. They're well ordered. But when you start talking about infinity, there's some really weird things that can happen, right? If I were to say the statement that infinity is greater than infinity, I could be saying something very powerful that's very true, because there are different infinities, right? Infinity is infinite. You just can't count it. Infinity plus 1 is also infinite. You just can't count it, but you know there's one more, right? So infinity is this concept. It's not a number, so you can't treat it as such. So when I see things like this, where the left-hand limit or the right-hand limit, yeah, they shoot up to infinity or maybe down to negative infinity, I feel satisfied saying infinity or negative infinity for a one-sided limit. But when it comes to a limit like this, technically you're still fitting the definition, but realistically, this is not an L, right? This is not some number L. That's not a finite number. So when you look at that, it really doesn't sit very easily, right? Because you're not locking it down to this finite letter L. So I've seen some people, and I'm totally okay with this, tell me that, yeah, from the left it's infinity, from the right it's infinity, but really this limit does not exist because there's no way to find it, right? Who knows how far up it is? But this is also okay because, look, they're agreeing. So technically you're fitting that theorem. You're not running away from that theorem at all. But do let me show you one very last thing, and I promise, was this an hour and 20-ish minutes? Good. I think we'll be right on time here. And I'm going to leave that up there. Let's compare this function, y equals 1 over x, without the square in the denominator. Here we go. Quick graph. Same problem happens. Vertical asymptote at x equals 0. But this is what the function looks like. And maybe I'll do a different color. I'll do purple. Same vertical asymptote, different looking function. Again, this was one of the toolkit functions we got in college algebra, or we've dealt with these. This is like the building block for all rational functions when it comes to pre-calc. Notice that the limit as x goes to 0 from the left of 1 over x is negative infinity. Notice that the limit as x goes to 0 from the right, so I'm putting a little negative above the 0 here for my left-hand limit. I'm putting a little positive in the power of the 0 there for my right-hand limit of this function 1 over x. Let me make that look a little straighter here. Yeah, it's positive infinity. I'm going to negative infinity from the left, positive infinity from the right. The limit as x goes to 0 of 1 over x does not exist. So in mathematics, we really want consistency. Notice the lack of consistency between here and here. Yeah, these limits both agree to positive infinity. They shoot up to positive infinity, but that's not a number L. That's just some sort of vague concept. Here, it is glaringly false to say that this limit is infinity or negative infinity or anything in between, because there's no way they're going to the same number. All right, so if any one of these situations happen, we call it a vertical asymptote because there's just a major problem happening around that x equals 0 in this case. But if the function shifted around or if it has multiple vertical asymptotes, it gets really hard to evaluate limits where those vertical asymptotes are. So we do have some limits that can just shoot off to negative infinity or shoot up to infinity. And again, for me, just to kind of be clear about this, infinity is not a number. So when you look at the theorem and it uses a specific number, capital L, if you don't have a specific number, capital L, this could be dangerous. Whereas here it is, hopefully to everyone, glaringly true that there's no way you're finding an L because they're complete opposites of each other. Right? But this one makes you feel a little woozy in your stomach, right? And I have seen some people tell me that this also DNE. They won't put infinity here. They'll say does not exist. And I like that because it's consistent, right? Infinity's not a number, so I can't, ultimately conclude that that's a number. But again, since they're going to infinity on both sides, the textbook actually has in one of these examples, and I'll see if I can dig it up real quick, but I don't want to waste time trying to find it. Or, you know what? It actually might be in a later section. Oh no, there it is. Example 8. And I'm surprised I had a hard time trying to find it. Example 8 on page 89, if you actually bought the textbook. It's looking at that limit as x goes to 0 as 1 over x squared, and it's saying, you know what, that does not exist. Right? So it doesn't call it infinity. It says, you know what, for consistency's sake, it's a vertical asymptote. Who's to say that one infinity is the same as the other infinity? Right? Maybe this one approaches infinity really fast, and this one really slow. Not to get into any sort of crazy stuff with infinity too soon, but so to wrap things up, limits disconnection between the value of a function, which is just that one point, versus a limit, which means you're sort of approaching from the left and the right, you're getting close. But think about, like, here I can't have my palms of my hands touch because they're only approaching each other. They can get closer and closer, but they never actually touch. Whereas that's a limit. A value is just plug it in. Right? One point, boop, plug it in. So make that disconnection, and then evaluating left limits and right limits separately, and making conclusions between, what does it mean to have a limit, and what does it mean to have a left limit and a right limit. Right? Look at that theorem about left and right limits and what you can conclude about the limit. Or backwards, look at the limit and see what you can conclude about the left limit and the right limit. And then just practice with some exercises. For right now, numerically, you're going to use your calculator and make a numerical table and see where they go, left and right. Graphically is another way to do it. You're going to sketch the graph and look for asymptotes or holes. If you graph on a calculator, it's going to be very hard to see. So you'll have to remember from pre-calc how to find the whole of a graph. And that's typically with a rational function where something's been removed from the domain. And then a little bit on infinity. We're not really getting too deep into the infinity stuff just yet, but sort of relating this vertical asymptote concept back into the picture. And like I said, in the future we'll touch back on horizontal asymptote as well. So that's section 2.2. Hopefully under an hour and a half. I am at an hour and a half and an extra minute and a half. So I need a minute and a half. So thank you very much, and I will see you for section 2.3.